Code word.
Code word, sorry you
Foot
didn't
of
understand
snow.
this in class and you have to watch it again. I know.
When you didn't understand anything, so you just do the homework wrong, and then you put the
Okay.
homework
That's
isn't
the reason why
great.
you
Oh no, no.
Data time.
It's broken. Miss Hellman, come on.
Fail. DXD right
Is the
there.
colon broken too? Because the
Oh,
R is like the R is like
It's a suspended period.
yeah.
This is R times.
Theta.
17 theta.
Yes.
Whoa.
Why is it 2 bars then?
I'm so good.
I don't know.
Because the times.
Apparently, whatever I used to make this in the update didn't transfer. So the length of an arc in a circle is given by R times theta. Thank you for knowing that. When theta is given in radians. Okay, that's actually something that I taught to my pre-calc classes on Tuesday.
Whoa. Sort of behind pre-calc.
Yeah.
It's kind of embarrassing.
Pick it up. Come on, guys.
Sorry.
Show me your moves.
Okay, and so we're talking about something that looks like this. And then this is our length. Okay? If we make theta super duper tiny, what's that going to look like? D theta. Think of like a two-dimensional shape.
Square? A
It'd be
rectangle?
like a triangle.
It would look more like a triangle, right? Line, itty bitty. Okay. So what do I need to fix here? So for a very small theta, the curve could be approximated by a straight line, and the area could be found by 1/2 base times height. Okay, if we make it small enough, it's going to look like a rectangle.
But
Ugh, triangle. Darby has me all messed up.
They're the
Sorry.
same thing in this. And
at what point is it considered very small? Like,
At
is it
one-
like
Less than a degree. I don't know. We're used to radians, so very, very small.
Kind of like when we make slices that are infinitely small. D theta would be infinitely small. So, if we use this for 1/2 base times height, we get 1/2 r squared for our area, for our change in area, excuse me.
Okay.
Just bear with me.
Soon we'll get to the integrals. Alright, rotate the cardioid around the x-axis.
Oh, we're not gonna rotate.
Few.
fingers?
We just have to revolve.
No, not that.
Okay? So, if we have all of these infinitely small triangles, we can add them together
No.
for our area.
Why does it use alpha and beta instead of A and B?
Because we like
Because we're getting quirky in Calc BC.
Well,
Actually, that's not even a beta.
what
that looks
is
like an
our
S.
input? What variable?
Theta,
Which is measuring
degrees.
measuring angles, right? And it's going to have to be in radians. Okay, it's going to have to be in radians. So alpha and beta are more Greek letters for our angle measurements.
And there's already a sigma in there because
Because we're
the
adding.
expression of
Yep, because the integral. Yep. So the integral, we're adding up all of those infinitely small triangles. Okay. Now, what you need to consider is when we are talking about area, okay, we are going to draw like these little itty bitty triangles and rotate through. So it gets colored in kind of like this. And we rotate through. So here, I've colored an area for, let's say, 0 to pi over 4. Okay.
Looks like an elbow.
I was gonna say that.
Oh, like this?
Yeah.
It's like an elbow
Okay.
that like has padding on it.
Or like a knee with a
Is that a
Elbow.
pad?
knee pad.
Actually, we should use the part of the elbow, the skin on your elbow, which is called the weenus.
Anyway.
That's an actual fact.
Okay. So anyway, I want you to keep in mind that we are going to always be drawing our area from the pole, and we're going to imagine our area being colored as we rotate through.
It is impossible.
Okay.
That's not true. Red marker will sure do that.
He can. He's done the break.
Please write down our first example.
Oh boy. That's all my feelings. If it's true.
Okay. What's nice about polar area, when we have a symmetric graph, we have some options. Okay, now we know that it takes us from 0 to 2 pi to create this graph, correct? Like if I start here at 0, we would have to go 0, pi over 2, pi, 3 pi over 2, all the way until 2 pi to get all of that area colored in. Okay, that kind of, it actually kind of looks pretty, but we would have to say 1/2 integral 0 to 2 pi of, I'm going to go ahead and write it as 2 plus 2 cosine of theta. Is that okay with everyone? Okay, that would be, what did I forget? Forgot that, I'm sorry. Okay, so 1/2 r squared d theta. Okay, we're going to go ahead and go from 0 to 2 pi, but it would be possible for us to do what else?
0 to pi and then double it.
0 to pi and double it.
I was finding dy dx like a fool.
Okay, area this time, Joe, area. Okay,
Hey, at
all
least
right.
I found it.
Now, we are going to have to really rely on our strategies from chapter 8 for our integration. Chapter 8, chapter 7?
Chapter 7.
Chapter 7. Chapter 8 is what we're doing next. No? Yes.
I don't know.
I can't keep track anymore.
What are we gonna learn another new
Eight was
type of
integration?
function?
Yeah, it was an
8 was integration. 8 was integration. So, chapter 8, we did a lot of trig integration. It's going to come back. All right? So, in order to do this integration, what are we going to have to do first?
Yes.
multiply it out. Like,
Yep.
square root.
All right. So, 4 plus 8 cosine theta
Why would it
plus 4 cosine squared.
be? I see.
Did you figure out your question?
Yeah.
Okay.
Foil. Dread. It's foil.
Then, can we integrate from here?
Yeah, I mean, it's not that hard.
We need our power reducing formula, yes. Do you remember it?
Oh. Oh, yeah, I guess, because the cosine squared.
Our cosine squared. No bueno. No bueno.
Well, couldn't you just make it a cosine cube?
No. Okay. What
Okay.
cosine squared is what?
1 plus cosine of 2 theta over 2.
It's like that. What's nice though about the power reducing formula in this case is since we're not using trig substitution, we don't have to change it back. Okay. So I'm gonna go ahead. Let's clean this up like a
Well,
lot.
like 6 plus 8 cosine of theta plus 2 cosine of 2 theta.
Okay, so this is gonna turn into a 6 because we have 2 plus 4
Yeah.
times 1/2. So can I make it 3?
Now it's 4 plus 4 times 1/2, which is 6.
But it's half.
Oh, you're getting rid of that one. Oh, yeah.
Yep. I mean, I'm just like simplify as much as I can.
Yeah, then that's.
And then this is 8 cosine theta, so I'll write 4 cosine theta. And then this would turn into 2 cosine 2 theta.
But then it just becomes regular.
I'll just do
because
like
the one-
4 steps at one time.
Do you not like that?
We're achieving nirvana.
Now, if you want to do that as a couple different steps, that's fine. If you don't want to worry about the 1/2 until the very end, that's fine too. Okay? But since everything was even, okay, maybe saves us a step in the end. All right? So what we have is 3 theta plus 4 cosine theta. Excuse me.
Sine.
That should change to sine. I was thinking sine, but looking at cosine, and so I wrote it. And then plus 1/2 sine of 2 theta. And we are going to have to evaluate that from 0 to 2 pi.
Okay, well, 0 plus 0 plus 0. 6 pi plus 0 plus 0. It's 6 pi.
So we're gonna do this in 4 minutes in class. It's gonna take me a while.
Yeah. Because we didn't.
Well,
because
but-
we won't do 20 steps at once, which is.
Well, we didn't do
Actually-
20 steps at one. Stop exaggerating.
Well, I mean, if we think about it, you did a ton of small, tiny ones.
Now, did anybody on their own decide to go from 0 to pi and double it? If you did, you would have gotten the 6 pi. Okay? Questions on that example? Limasones without a loop are very straightforward to find the area of. Why would the loops not be straightforward?
Well, because you have to subtract that area.
Tomorrow is when we'll look at a loop.
Is it because you have to subtract that area, so you take one integral minus another integral?
Yeah, we would, like, you would be asked to find, like, the area in between the loop and the outer, okay, or find the area of the loop. And so you would have to know where the loop starts and ends and all that kind of stuff. Okay, but luckily limasones are symmetric, and so we can use that to our advantage. Okay?
They kind of look like turnips.
Okay. Let's talk about roses.
Oh,
Now this is nice. I'm only asking for 1 petal.
are you sure? Are you sure it's nice?
It looks like it's about.
About 1? Just 1?
I'd say about 3. About. We're just gonna. What if it's?
It looks like
Why don't we just take the entire domain and then divide it by 3?
it looks like pi. To be honest with you.
I'm going to guess that it involves pi.
I'm gonna guess.
Well, like
Pi.
if I were
It's
if I
about
were to make
three.
an educated guess just based on the image, it looks like it's about pi.
Okay, which petal would you like to find the area of? Does it matter?
Probably
The bottom one, because it's the second
bottom
one.
right one.
There's only one bottom.
you have some options. Are these petals symmetric? Yes. So like no matter which one you pick, even if it were like this one, right, we could start finding the area, and once we got to here, we could double the area. Okay. Now, this is cosine, correct?
Oh, so we could
So
just
this is
go-
our first coordinate. So like this is the area like we would start for finding at 0. So you really wouldn't be able to have a nice integral to find that 1, but could we find half of it?
Well, yeah, because to find that 1, it ends at 2 pi. Yeah. Or it doesn't.
Well,
it-
you-
go back from before 0.
You would have to go like a negative.
Yeah.
You would have to find one of the zeros that were negative and go from that negative 0 to that positive 0. But we do need to figure out where we are at when we get to the pole so we know where to end. So when you are finding the area of whether it be one rose petal or multiple rose petals, we need to know the 0 so we know where the petals begin and end. So please take a moment to find me the 3 zeros of this rose curve. And we'll talk about our different options. Check with your neighbor to make sure they got the same thing.
Okay, I think alright, voice was done. Technically, there's 6 from 0 to 2. But no one goes to 2 pi because it just over.
Annalie, where are our 3 zeros?
Chair there.
Pi over 6.
Oh, sure.
Table
Yes.
is 2. Pi over 2 is and 5 times.
Hubert.
Okay, so we can do a few different things. We can find a petal, and we can the area of a petal by going from pi over 6 to pi over 2. We could go from pi over 2 to 5 pi over 6. We could go from 0 to pi over 6
And multiply it by 2.
and double it.
So just get rid of the 1/2.
So yeah, the 2 times 1/2 goes away. I don't know about you, but I like plugging in 0 to sines and cosines over plugging in pi over 6's because they come up with nice numbers. Now, the pi over 2 would be nice, right, in this case, but let's go from just so you have another option, 0 to pi over 6, and we'll take 3 cosine of 3 theta and square it.
Plus 9 cosine squared of 3
So yes, the 2 times 1/2 cancel out, and we end up with 9 cosine squared of 3 theta. I guess I'll ask you, do you want the 9 inside or outside? Outside?
Yeah, because then we don't have to deal with 9/2.
Okay. We're just have to deal with 1/2, right? Okay. So, as you can kind of anticipate, you're going to use the power reducing formula probably often. Okay. So for cosine, we would need to change it to 1/2 plus 1/2 cosine of
6 theta.
6 theta. We would double it.
Why are you just going to give us a radical cosine so we don't have to power reduce?
So we have 9 times 1/2 theta plus, what's the antiderivative here?
Sine of 6 theta over 12.
Oh, this is open. Okay. Setting up the integral is what I'm most concerned about. That's the new stuff here. It gets tedious though when you get to the evaluating, and you're just going to need to be careful, make sure you're plugging things in correctly, make sure your arithmetic is correct.
But thanks to the pi over 6, the sign will be a 0 when we plug it in both times.
Okay, so we get pi over 12
Plus 0.
plus 0.
Yep, because sine over 6, sine times 6. 6 pi over 6 is pi, which is 0 from u. That's 3 pi over 4. Wee. That wasn't so bad.
So almost 3. Is that you, right? That's what you guessed, 3?
Yeah. I'm pretty good at this whole guessing thing.
Did anybody on their own go from pi over 6 to pi over 2?
It would be the same.
It would be the same thing. Now, let's talk about if I asked you for the area of all the petals.
You just multiply by 3.
Okay, yes, find one and then multiply it. Okay, or in this case, we could have found a half of a petal and multiplied it instead by 6. Okay.
Nice. It's 9 pi over 4. That's the area.
Oh, of the whole thing?
Yeah.
Oh, I was like, it wasn't. Got it.
Yeah.
Okay. When we were in our parametric unit, we talked about arc length.
Yeah.
How did we find arc length?
Using calculus.
Square root of 1. Okay, so I guess in normal, so Cartesian, it was 1 plus dy dx squared.
Oh, is it just
What
that?
about in parametric?
Wasn't it the same thing?
No.
I was just gonna combine them.
What do you think's going to happen?
I hope nothing.
It's gonna be dx data plus y data.
Yes.
Well, first we have to
Yeah.
consider that everything's in terms of theta, right? So we're going to have to go d theta in our integral. So if x is our cosine theta and y is our sine theta, then this happens. And we could go through all the math,
Looks like we're gonna go through plenty of math as it is.
or we could just accept it for what it is.
I don't want to accept it.
Okay, but we do.
Knock knock. Who's there? The derivative of e to the x. E to the x.
It's like that Spider-Man.
Yeah.
It's like,
The integral integral of e to the x. The derivative of e to the x. E to the x. Spider.
Okay. You ready for a lot of math?
No.
Do you have this written down?
Yeah. dr d theta. Oh, is that dy theta?
That's using that two eyes.
Does it have to specify above the x-axis?
Well, not all of it is above the x-axis.
Well, no. Obviously above the x-axis.
Let's just move it up like one unit.
Now I'm going to tell you that when you do arc length, you're going to want to use symmetry as much as you can. You want the smallest window for your limits of integration as you can possibly get. So instead of going from 0 to pi, what could we do to make it even a smaller,
0 to pi over 2.
and then double it? Okay, so this is what we would have. R squared plus R prime squared. What's R prime?
dy over dx.
When we talk about, it's going to be dr d theta. So instead of dy dx, we get to use dr d theta.
So we can just derive that directly. Okay.
Correct.
And it's just cosine.
Correct.
Yay, power reducing.
Let's use, so this would be 1 plus 2 sine theta plus sine squared theta plus cosine squared theta.
It's just one.
Okay, now we can just change it into, that's 1. Okay, so we have 2 plus 2 sine squared.
Just 2 plus 2 sine theta.
2 plus 2 is 4.
Because sine squared plus cosine squared is 1. 1 plus 1 makes 2.
You can factor out the 2 and then you have like
Yeah,
the
but
original
now,
R
now we
equation.
have to deal with the radical.
Yeah, and this might not be bad. We can factor out radical 2. So then we only have 1 plus sine theta.
Which
2 radicals.
And this is where you're probably not going to be like, too excited. Like, we can't really use U substitution for this
Radical time.
composition because we don't have anything left over for that U substitution.
Let's factor up 0.
We have the strategy of multiplying by a conjugate.
wow.
Why? Let's just talk about it. When we multiply by a conjugate, when we have things like 1 plus sine theta, 1 minus sine theta, we force what identity to happen?
Difference of squares.
Which fits well with the Pythagorean identity. Okay? So I know that I need to use U substitution here, but I can't, so I'm going to force it to happen. So we're multiplying by a well-chosen 1. All right? And I'm going to do this really slow here. So this is going to take up some work, and I'm sorry, or some room. I'm sorry about that. Now, what is 1 minus sine squared? Okay. So 1 minus sine squared is cosine squared. Okay. Now we do have to be careful here. It is not always as simple as the square root of cosine squared is cosine. Because when would that not be true?
Inside is negative.
So in the second quadrant, cosine is negative. Do you agree? If I did the square root of cosine squared and I plugged in 2 pi over 3, it would not be equivalent to the cosine of 2 pi over 3. Okay? But luckily, where are our limits of integration? They're from 0 to pi over 2. That's the first quadrant, correct? So since we're going from 0 to pi over 2, it is legitimate for us to call this a positive cosine of theta.
So for some reason you did pi over 2 to pi, it'd be negative cosine?
Correct. Correct. Okay. So now we have something that's set up very nicely for u substitution. U could be 1 minus sine of theta. Oh. Which makes du negative cosine theta d theta.
So now it's just negative 2 radical 2.
Yeah. So negative 2 radical 2 u to the negative 1/2 du. Some of you like to change your limits of integration and just stick with the u's. Some of you like to change back to the thetas and then plug in your theta values. That's fine too. Whatever is your method, your arc length ends up being 4 radical 2. So I'll let you work through the rest of that, because some of us prefer different methods. From here, see if you can get to that 4 radical 2. Uh-oh. I don't have a mouse. Oh, no. Well, we might not get this video.
Oh,
Well, my mouse
does it become cosine
isn't clicking anything,
reasons?
so I'm going to have to force...
Okay, but even then, there's still a 0 no matter what, because it's 1 minus the... Yeah, I'm confused. Is it theta minus the thing?
Oh, maybe.
No?